All right, so let's look at this question. This question feels familiar. I think this is the exact same setup we have for our dynamics lab, which is great. So doing this question from scratch should be a great exercise for you. So as a reminder, so we are going to be using standard strategy. The moment I notice it's dealing with the forces and that we have to somehow figure out acceleration using forces, that's the moment I would jump into standard strategy steps, which are one, draw free body diagram, and two, define axis. And there's some care that we take. I will mention those as we define axis. And three, we um, break forces into components, into x and y components. And finally, after we are done with the steps 1 through 3, we should have a free body diagram that contains all the information we need. We write down Newton's second law equation. Acceleration is given by net force divided by mass. So let's start out with a free body diagram. And I'm jumping straight into this strategy without really having read through the question carefully, because kind of what details of the question they ask doesn't matter. No matter what they ask, this is the steps we need to go through anyway. So let me go through these steps and then read the question. So our free body diagram is, we have two objects, so we'll need the free body diagrams, two diagrams. So I'm gonna plan on drawing one for mass M1 and a separate diagram for mass M2. So as you draw free body diagrams, this is what you should be doing. You should draw the forces that you know are there and then ask yourself the question, did I draw all the forces? So let me start out with a few forces that I think should be there. There should be gravity. There's always gravity. And since in this picture I see strings attached, there's gonna be tension forces. So let me draw tension force on the first block, T1, and tension force on M2, T2. Kind of, you always draw tension along the direction of the string pulling, away from the point where it's attached. And then you ask the question, did I draw all the forces? I think with the M2, I can easily convince myself that I did draw all the forces because from the description and my intuition, I know acceleration points downward. And with these two forces, I can imagine arranging them in such a way that they will give me a net force downward. So that's good. With the M1, I'm not convinced that this is all the forces because adding these two, acceleration will go this way, and that's not the acceleration I was expecting. I'm expecting an acceleration that's going to the right. That's the way it's drawn in the figure, and that's what my intuition tells me. So thinking about this setup for a little while, I remember, oh yeah, I need to draw my normal force. Yeah. So this normal force will cancel out gravity and basically allow T1 to be the net force. That's how it'll work out. So, okay, I feel like I've drawn all the forces. We are done with the step number one. All the forces we've drawn, it's consistent with our sense of where the acceleration should go. In step number two, we should define axis. And as you define axis, really what you're looking at is your direction of acceleration. So let's say, since for object one, our acceleration points this way, let's make this our plus x direction. And in case it matters, let's say y direction is that way. This is our normal straight axis. And for the object number two, now you can define axis independently for each object. So this axis doesn't have to be the same axis for this. So I'm gonna use that freedom to define downward to be plus x for the mass two. And I guess I could also define y direction, but here I don't have anything interesting in that direction, so I don't really have to worry. Okay, I defined my axis. And three, break forces into components. Here I see some simplification. All my forces are already in the direction of one of the axes. So I don't have anything I need to break down. So I'm just gonna leave them be. Step number four, we write Newton's second law equations, and we need an equation for each direction and for each object. So with the two objects, with the potentially two dimensions, we have potentially four equations, and, and let's see what they are. So we are going to need equation for acceleration of mass 1 along the x direction. So for that, we have x direction force, T1, and no other force. So that should, so acceleration is equal to the net force divided by mass. And this mass is always the mass of the object that you've drawn the free body diagram for. So here it should be m1. So that's one equation. Equation number two, I need a y direction for acceleration of the object one. So y direction. Now the way we defined our axis, we've purposefully made it so that the acceleration in the y direction is zero. So this is going to be zero. That helps to simplify our expressions. And we would write down, okay, the net force in this direction, that's going to be N1 minus M1G, N1 minus M1G divided by the mass of the object, so M1. Okay, that's two equations for object M1. Now I need to write down for object M2. I have acceleration of object M2 in the x direction. My net force is M2G, that's in the plus direction. M2G minus T2, that's in the negative direction, divided by m2, the mass of the object I'm writing these equations for. And as I think about writing down an equation for a to y, I get something that's very boring. So the way I set my equations, I know my acceleration will be zero. And there are no forces in that direction. So I get zero is equal to zero. All right, I think I knew that before I had to write anything down. So I won't bother with these. This fourth equation. So this is the end of the standard strategy set of steps. We've written down Newton's second law equations, and let's see if we have enough number of equations for the unknowns we have. So it looks like the question will be asking for acceleration of the blocks. So I don't know this, and I don't know this, two unknowns. And it's gonna be asking for tension. I don't know T1. I don't know T2. Four unknowns. um, and looking at the rest of my equations, I also don't know N1. Um, so five unknowns. I have five unknowns and three equations, um, which isn't enough. So this is where you should spend a little bit of time to think through the setup and see if you can simplify it a little bit further. Um, I think one thing that a lot of people will get intuitively if you take the time to think this through is the relationship between acceleration A1 and acceleration A2. These things are connected by a string. They're kind of going to be moving together. So as they move together, well, the magnitude of acceleration will be the same. So instead of writing these two separate symbols, we can say, well, let's just call them both A. That's the acceleration of both of the blocks, the magnitude. And that's the quantity that will go here. So I reduce the two unknowns down to one. And I have the two unknowns T1 and T2. And this is where some of the things that they say is significant. We haven't quite covered enough physics to highlight why they are significant, but where they say the pulley is frictionless and massless. It For now you can think of it as an authorization for you to treat the tension on this side of the string and the tension on this side of the string as being equal to each other. So where we label them as T1 and T2, and I labeled it that way because that's a good problem-solving hygiene. It's a good habit building for making sure you use different symbols for quantities that are potentially different. And for this specific setup, this description is authorizing you to set T1 is equal to T2. So here, instead of using those subscripts and having them count as two unknowns, let's just get rid of the subscripts and just have that be the one unknown T. And that's what will go here. So, okay, we've reduced our five unknowns down to three and eliminate two of them. So we have now three equations, three unknowns, and one, two, three equations. So we should be able to solve them. And I think I've demonstrated doing this by hand. Let's do it using computer algebra system. And because I'm using computer algebra system, I'm also deliberately not doing some of the simplifications that I could have done and just choosing not to bother. Let's just let the calculator handle it. It's like, you want to calculate um, 10 times 2. If you think about it for a bit, you realize, oh, I could do that in my head. But here, we have a calculator. Let's not do it in our head and just be lazy. Or not. So, okay, acceleration, that's going to be these two accelerations. Tension, that's going to be these two tensions. And I need the symbols for M1, mass of the first mass, M2, mass of the second mass. And then I need a symbol for N1, the normal force on the thing. And I don't really want to write down A1Y because that's going to be 0. I think I need a G. I think that's all the symbols I need. So with those symbols, we'll write down our equation. Let me just reuse our variables. So equation 1 is acceleration is equal to t divided by m1. And equation 2 is that equation there. So 0 is equal to n1 minus m1 times g divided by m1. And equation 3 is that equation here. Acceleration is equal to m2 times g minus t divided by m2. Okay, so those are all my equations. Let me just double check that they seem appear entered right. That's my first equation, second equation, third equation. I think they're all right. Okay, so let's solve. So I'm going to solve for this system of equations. And I'm going to solve for my unknowns, which are, let's put them in the order I want them. Acceleration, tension, and I need this unknown, N1. Okay, let's see what it, oh, that was quick. So I get acceleration, tension, N1. Great. Oh, yeah, of course the normal force is just M1 times G. That's silly. I could have omitted that, but that's fine. So um, so let's go through this. Let me define solves. That's gonna be my previous output. The first element because it's a nested thing. So when I do that, that's yeah. So the first element of that'll give me the acceleration, and I can substitute in the values that I have, which are I'm given the mass on the table is that's M1, that's a 4.6. So M1 is 4.6 kilograms. M2 is 1.5 kilograms, and I need a G of 9.8 meter per second squared. Um, okay, I think that's all the numbers. Let's see if I put that in. Yeah, acceleration is 2.41 meter per second squared. Let's try the, let me just copy and paste this. Um, all right, so this is solution for tension. M, M2, okay. Um, so tension is 11.1 Newton. Oh, I'm not done. Let me enter A and B first to make sure I got acceleration and tension right. 2.41 and 11.1. And I'm not done yet because where it says the block M2 hits the floor with some speed. So this is a kinematics question. So reading back, I think, let's see here, if it starts from rest and is initially located some height from the floor. Okay. So we've solved acceleration there. Let me just um, define my acceleration as that. That's my, just gonna type 409836065573. There's a better way to do it. So I have acceleration. So it from the information I have, I'm given the distance it travels, and I'm asked for speed. It feels like the quickest way to do it is to use the v squared formula. V squared formula goes as, v final squared is equal to v initial squared plus 2 times acceleration times the distance it moves. So if I want just the final speed, it'll be square root of this expression. So let me just do that. I have square root of, my initial speed is going to be 0 because it's starting from rest. 2 times the acceleration, that's the acceleration I copied from above. That's the acceleration that we figured out from solving A and B. And the height, the distance it travels will be 0.9 meters. And I made sure to enter everything in basic SI units. So when I enter this, I get 2.08. It should be in basic SI units, so 2.08 meter per second. And let's make sure. Yep, that's it. So that's the question. It's the again the setup for the dynamics lab, and this is I feel is you should set up a situation like this often because I feel it's a good practice for standard strategy. Really, our goal with the standard strategy is where you you are so, I don't know, used to it, so practiced with it that all of these steps eventually feel very mechanical. If there's any challenges in doing the algebra at the end, use computer algebra system so that so that you can focus on getting the physics practice that I think everyone can use.